Greetings, chemistry students. When we last left off, we were talking about the ideal gas law, and I've got a little lab that I'm going to demonstrate for you. And as you watch the lab, pay attention to the data points that I record. It may be helpful for you to write them down. And then when you come back to this video with me, we're going to actually work through using the ideal gas law how to figure out what the molar mass of this gas is. And the key thing for that is that molar mass is grams divided by moles. So we need to figure out how many grams of gas we're working with, and we need to figure out how many moles of gas we're working with. And based off the ideal gas law, since N is moles, we can solve for moles and do some simple division and figure out molar mass. For today's demonstration, I have an ordinary lighter that I have removed most of the parts that make it work now. So I've disassembled this lighter. It's essentially now just a canister of lighter fluid with a little button that we can push to release the gas. So for this experiment, I'm going to zero out the scale. I'm going to weigh this lighter and see how much it weighs. And it looks like this lighter weighs 12.687 grams. So over here I've got a tank of water that I've added some red food coloring to help you see, and I've got a 100 milliliter graduated cylinder. Now I'm going to fill completely full of water and then invert it. And what I'm going to do is I'm going to add the gas from the lighter to the graduated cylinder by putting the lighter underneath and then depressing the button and slowly bubbling the gas in to collect it.
So I am slowly filling this cylinder up with butane gas.
I'll stop right there. And it looks like we have collected, it looks like I've collected 99 milliliters of gas from the lighter. Now the other thing I'm going to do is I'm going to measure the temperature of the water, which should be a good proxy for the temperature of the gas, and I'm going to measure the atmospheric pressure, and those are displayed right here for you on the LabQuest screen. So we're at like 99.95 kilopascals, and the temperature is 23.3 degrees Celsius. So now I've collected the gas, so we know the volume of the gas, we know the temperature of the gas, we know the pressure of the gas. So with that, we can calculate moles. And then I'm going to let this gas go. We don't need it anymore. The only thing I've got left to do is dry off the lighter and see how much it weighs. Okay, I've dried off the lighter, and I'm weighing it now, and it weighs 12.485 grams. All right, so from watching the video, you should have found the following data points. So we have the mass of the lighter before and the mass of the lighter after. So we can figure out the mass of the gas through some simple subtraction, and the mass of the gas comes out to be 0.202 grams. Now, the other things that we know about the gas, its volume is 99 milliliters. But in the ideal gas law, we have to use liters, and in liters, we divide by 1,000. There's 1,000 milliliters in a liter, so this is 0.099 liters. Then for pressure, at 99.3 kilopascals, and then for temperature, it's 23.3 degrees Celsius, which in kelvins is 296.3 kelvins. So given this information about the gas itself, we can say that N equals PV over RT by solving for moles in the ideal gas law. And so we take our pressure, which is 99.93 kilopascals, times 0.099 liters, divided by the gas constant, which is 8.314, and the temperature 296.3 kelvins. Put all that into our trusty calculator, and we come up with 0.00401 moles. Now, the molar mass is grams divided by moles. So we take our grams and divide it by our moles. And we do a little bit of simple division, and we come up with 50.37 grams per mole. And so that's the answer we're getting. Now, the problem with this is if you do a very simple Google search, you'll find that butane, which is the gas that was in the lighter, is C4H10. And butane has a molar mass of approximately 58 grams per mole. So the question for today that I'm asking of you is, why do you think that I didn't get 58 as my answer when doing this experiment? What's something that I might have done incorrectly or not perfectly in this lab that led me to get a smaller molar mass than the actual value? So there's going to be a question attached to this assignment in Google Classroom. Tell me what you think. What might I have done wrong? The other thing I want to do really quickly is talk to you briefly about the states of matter. There's not really going to be a worksheet on this or anything. I just want to make sure you're familiar with this. You're familiar, I'm sure, with solids, liquids, and gases, but there is a fourth state of matter that some people seem to not really know exactly what it is, which is called plasma. So I'm just going to kind of run through this. The PowerPoint is already posted in Google Classroom. But in a solid, the particles are very tightly packed together, so they can't really move. In a liquid, there's a little more room between them. Gases, the particles get really far apart. And plasma, even further apart. In a solid, it may not seem like particles in a solid move at all, but they really do. They just can't move very far. They don't have what's called translational motion. They can't go from one place to another because they're surrounded. It's like they're kind of like in a particle mosh pit. They can't really go anywhere. They just kind of vibrate in place. They move around a little bit, but then they bounce off of their neighbors and kind of just end up in the same place. In liquids, the particles can float past each other. In gases, they can kind of move randomly all over the place and quite fast. And plasmas, even faster. The next two columns are asking whether these things have defined shapes and volumes. For solids, as you're probably aware, you can define the shape of a solid. For instance, if you have an ice cube, that's a cube shape. Liquids don't really have a defined shape. They take on the shape of their container. Same with gases. and with plasmas. For instance, with gases right now, the air in my office here has the shape of my office, and if I breathe the air in, it then has the shape of the inside of my lungs. So gases kind of they take on whatever shape of whatever they're in. Now for volume, solids have a defined volume. Liquids also have a defined volume. If you have a gallon of milk in a gallon container and then you spill it on the floor, you have a gallon of milk on the floor. And if you put it back into the container, its volume hasn't really changed. Gases, however, their volume can change. You can take a gas and squeeze it into a smaller volume. Same with plasmas. The last couple of things, I'm not sure what happened with the formatting on this slide. Asking if things are compressible. Solids are not really compressible, neither are liquids. Now, they are technically to a very small extent, but not nearly as much as gases or plasmas, where since there's so much space in between the molecules, you can squeeze the particles closer together. For a diagram, this is not super important, but solids, the particles are really, they're kind of form their own shape. They can hold themselves up. Liquids, they kind of sink down towards the bottom of their container. Gases, they're spread apart, and plasmas even farther apart. Then just to go through a couple of examples of these things. Examples of solids are a book or a rock. There's lots of other examples, a phone. Liquids include water and milk. For gases, you've got oxygen, helium, carbon dioxide, water vapor. All of those things are gases. And then for plasmas, the sun, the stars, neon lights. Inside of fluorescent lights, there is a plasma of mercury vapor that gives off the light that ultimately is what you end up seeing. It's a little more complicated than that. But plasmas are essentially high energy gases where the electrons have kind of been stripped off of the atoms of a gas molecule. So that's essentially what plasma is. Wouldn't worry too much more than that for this course. So that's all I've got for you today. Tomorrow, we're going to start looking at what happens when you apply energy to solids, liquids, or gases, and we're going to quantify those things with specific amounts of energy and specific temperature changes and all that good stuff. So that's all I've got for you today. Don't forget to answer the question that's in Google Classroom.